Hi, I'm Elaina Landrum. I'm in Professor Schatz's Physics 2 section, and this is my Lab 3 report. This lab mainly focused on the magnetic fields of bar magnets and how distance and observation location affects the magnitudes and directions of the magnetic field at that point. Some important concepts from this lab include the Biot-Savart law, because this is used to derive the formula for finding the magnetic field of a bar magnet. It is also crucial to understand how distance affects the magnitude of a magnetic field. The principle of superposition is also important because at the beginning of the data collection, we have to align the magnetometer so that the Earth's magnetic field doesn't interfere with the readings. The actual procedure of the lab consisted of finding the location of the magnetometer in the phone and then using an app to measure distances where the x component of the magnetic field reading is a certain value. Then using that data, we can calculate the magnetic dipole moment mu and plug that into the computational model to determine the off-axis effects of the bar magnet's magnetic field. My results for the in value, mu, and the predicted and observed B net values at 45 degrees are listed below. The spreadsheet section on the left is where I recorded my data from the various trials of the experiment. There were 3 trials each to record the distances at which the x component of the magnetic field yielded readings of 20, 70, 120, 170, and 220 microtesla. Then the spreadsheet section at the bottom shows the off-axis data I collected, which has been corrected for possible interference by the Earth's magnetic field. The graph shown has plotted the natural log of bx versus the natural log of the distance r, and from this graph we know that the slope is our calculated n value and that the y-intercept equals the natural log of constant k. The correct value of n is known to be -3, and my observed value of -2.976 is very close to that. From these numbers we can solve for the magnetic dipole moment mu, which I'll explain more on the next slide. The first equation shown here is the equation for finding the magnitude of the magnetic field of a dipole with an observation location on axis, and the second equation is a simplified equation for finding the magnitude of a bar magnet. Since the magnet we used in this experiment is a bar magnet with an observation location on axis, we can set these two magnitudes equal to each other. Since we know n equals -3 as discussed on the previous slide, we can simplify the equations further by canceling out the r cubed in the denominator. Now we arrange the equation to solve symbolically for mu. Since we know natural log of k is our y-intercept from the graph on the previous slide, we can calculate k and plug it into this expression for mu, along with the constant mu naught. The purpose of the code in this lab is to provide a visual model of the bar magnet's magnetic field, modeled with arrows at various observation locations to show how the directions and relative magnitudes change with the location of the observation point. In order to model these arrows, I had to write a function to determine the magnetic field at a certain point. The function, which I've included a screenshot of, takes in a magnetic dipole moment vector mu and a location vector r and outputs a magnetic field vector b. In the visual representation of the magnetic field, the orange arrows are at locations on axis while the blue arrows are at perpendicular locations. This explains why the orange arrows have twice the magnitude of the blue arrows, as well as why the orange arrows are pointing in the opposite direction. The green arrow in the top right corner represents the magnetic field at a 45-degree angle and distance 0.252 meters away from the magnet. I had to scale this arrow by an additional factor of 10 just for it to be visible, so this magnitude is quite small relative to the closer on-axis and perpendicular arrows. Comparing my calculated and measured values for the magnetic field at the 45-degree axis, my calculated value is 2.01 times 10 to the negative 5 Tesla, while my observed value is 5.23 times 10 to the negative 5 Tesla, which is over twice the calculated value. I'll explain this discrepancy more on the next slide with the post-lab questions. My calculated and measured values for the 45-degree angle magnetic field were quite different. I think this can be attributed to the error of not resetting the magnetometer app after every use, as well as possibly not aligning the phone correctly to cancel out the effects of the Earth's magnetic field, as this could have altered the x and y component readings. The two observations I noticed during this experiment are that when the magnetometer in the phone is a considerable distance away from the magnet, the x component reads near 0. Additionally, as the magnetometer gets closer to the magnet, the x component of the reading increases. Overall, this lab really focused on the applications of Biot-Savart's law and the relationship between magnitude of the magnetic field and distance of the observation location, as well as how the principle of superposition plays into summing up parts to calculate the net field. This lab also really helped me understand how to visualize a magnetic field and how to know the relative magnitude as well as what direction the field will be pointing in at a certain observation. Overall, this